An important part of electrochemistry is electrolysis, where you are applying an electric current to force a reaction to go in a non-spontaneous direction. And non-spontaneous is kind of ambiguous terminology. It doesn't mean the reaction won't happen, it just means the reaction won't happen in the direction you wrote it. It is spontaneous in the other direction. And that's the problem. So if you have a reaction that's spontaneous, like a battery discharging, you turn on your phone and over time the battery discharges, eventually it's going to stop sending electrons in that direction and it won't power your device. And the solution is to force the reaction to go in the non-spontaneous direction, the reverse direction. And you do that by applying an electric current with a charger. So the battery spontaneously discharges to power your device. If you want it to go in the non-spontaneous direction, the reverse direction, you're going to apply a current and force the electrons in the other direction. And when you're looking at electrolysis calculations, there's a few basic units that can be combined together to get dimensional analysis in a very convenient location. So let's look at the basic units you would be working with for electrolysis. You have to worry about electric current. Okay? Current in general for chemistry and physics, you're looking at the variable I, and units on that are going to be amperes. All right, capital A, which is a coulomb per second. All right, so current's going to be a big deal, and you can kind of plan ahead here, like you are applying a current, and you're going to apply it over some amount of time. So time is going to be another big deal here. And obviously, lowercase t, and our units on that are going to be seconds, if we want to work with our amperes as a coulomb per second. So looking here, we've already got we've got seconds and seconds. We still need coulombs, which is a measure of electric charge. All right. Generally, you'll use a lowercase or uppercase q for this. In electrochemistry, it's a little dangerous to use the capital Q because that's used for reaction quotients in equilibrium problems, and that's a pretty big deal. So I'll use the lowercase q here. The units on this are going to be coulombs, right? And that's a capital C. And where is this charge coming from? If we're dealing with electrolysis reactions and we're dealing with electrochemistry, the charge that we're dealing with, right, this is coming from electrons. And you may think of that as it's like due to the electrons. So why do we have a charge? We have a charge because we're using electrons. And so it would be nice if we could somehow relate our charge to some number of electrons. And it's Faraday's constant that allows us to do that. And that's a capital F when we're looking at the symbol. And the value of that is 96,485 with units of coulombs per mole of electrons. So as you look at this, this is the total charge we will be dealing with. It's calculated, or it's related to the electric current and the amount of time, and we can correlate that to some number of moles of electrons. But now we have a new variable to work with in the dimensional analysis. So we need to somehow turn this into, right, moles of electrons, and I guess moles as a whole, variable n, is going to be critical for us. So moles n, and the units on that are moles. And when we're talking about moles, the two things we're going to have to relate, and this is the big idea behind electrolysis calculations, you can have moles of electrons, right? That's going to match up right there. And you can have moles of whatever your species is, right? So your aluminum ions or your zinc ions or whatever. And these are going to be related by the half reaction. So that's going to be stoichiometry or dimensional analysis taking care of that. And then in the real world, we don't usually just deal with moles of some species. In the lab, we would deal with a mass. So I think we can sneak that unit in at the end there, mass. And we'll do our mass in grams. But we could do it in kilograms following the SI standard. All right, so with this in mind, I kind of want to set up how these equations are going to work, and then we'll take a look at some specific equations. the first thing you need to consider for the dimensional analysis of electrolysis reactions is our current. Since it is amperes or coulombs per second, we can get right to our coulombs by multiplying by time. So current times our time, right? So our current's going to be in coulombs per second times seconds, and that's going to give us a charge. All right, and that charge is going to be in coulombs. Now, since this charge here is the result of our electrons, right, we can convey this charge in terms of a number of electrons, right? And we do that using Faraday's constant. So we'll take this charge and we'll bring it down and say, okay, I have some charge total, and we're going to divide by Faraday's constant, and that's going to give us some number of moles of electrons. And we see total charge in coulombs, and we divide by coulombs per mole of electrons. Coulombs cancel. Moles of electrons is in the denominator of the denominator, which is the numerator. When you divide by a fraction, you multiply by the reciprocal. So it makes sense that you would have some number of moles of electrons. And that by itself isn't super useful, but we can turn that moles of electrons into moles of our species using the half reaction for the cell. So for example, in this case, let's say we had zinc 2 plus 2 electrons going to solid zinc. We would have a 1, well, let me try that again. We would have a 1 to 2 ratio there, and we could say for every 2 moles of electrons, there's 1 mole of zinc. And that would get us moles of our species, and then usually at the end we would sneak in a molar mass to get us to grams of our species. And for zinc, the molar mass happens to be 65.39. So 65.39 grams per mole. All right? And if you look at how that works out, moles of electrons are gone, and then moles are gone, and you just have some number of grams of zinc. All right? So once again, current getting us charge, charge getting us moles of electrons, and moles of electrons eventually getting us a mass of our species. And let's see how that works with a real problem. We'll just make up some numbers here that are convenient, and we'll say what mass, and we'll go with our zinc from before, of zinc may be precipitated when, we'll say, 3.0 amperes of current are applied to a zinc nitrate solution for some arbitrary amount of time. Let's just say 6,000 seconds, all right? I'm going to start out with a number or an amount of time in seconds just to save that one-dimensional analysis step later. A few things we want to take note of, and I think this is a very, very, very important step that might get overlooked. Zinc. I'm not worried about the spectator. These are zinc ions in solution. As soon as that zinc nitrate hits the water, it dissociates into zinc ions and nitrate ions. I'm not worried about what the nitrate ions are going to do. They're spectators in this case. I'm very worried about what the zinc ions are going to do. And they're going to follow the reaction that we wrote a little while ago, Zn2 plus 2 electrons going to zinc, all right? And this number right here is super important. That's our N, our number of moles for the actual stoichiometry. Other things to note in advance. An ampere is a coulomb per second. So I'm just going to declare right there that I'll write coulombs per second. And we'll set it up in a not strictly dimensional analysis way, but I've got 3.0 coulombs per second. And if you look at that, you can see seconds are going to be easy to remove if we multiply by our 6,000 seconds, right, over 1 or whatever. We currently have coulombs, and we can take this resulting number and we can divide by Faraday's constant. So if I divide by 96,485 coulombs per mole of electrons, the coulombs are going to cancel, and we're going to end up with some number of moles of electrons. And this calculates as 0.186 moles of electrons. And like in terms of sig figs, I guess it'd be 2 with the numbers I gave, but we'll just say 0.186 moles of electrons. All right. So that doesn't seem like many electrons, but remember a mole is 6.022 times 10 to the 23rd. So we're dealing right here with a number to the 22nd power, which is a bunch of electrons, right? So our 0.186 moles of electrons, we happen to know there are 2 moles of electrons for every 1 mole of zinc in this reaction. And then we go one more step and we say, oh, for every 1 mole of zinc, there are 65.39 grams of zinc. And we can follow moles of electrons are gone, moles are gone, moles are gone, and we get grams of zinc, which in this case ends up about 6.1 grams of zinc. All right? So what we're saying is if we take a zinc nitrate solution and apply a current of 3 amps for 6,000 seconds, we're going to get 6.1 grams of solid zinc precipitated out. And that's the basis of that. I'd like to look at one more example where we're looking for something other than mass, maybe like a time, and see how the dimensional analysis works there. An example I like to use for charging currents or electrolysis currents is like what cell phone chargers work with. And right now it's not uncommon to be in like the 2 to 3 amp range. So let's pretend we're hooking up like a cell phone charger to some aluminum or silver nitrate solution so we can get some silver out of it. And we want to see how long it might take to do that. So we'll say how much time is required. To obtain, and I don't know, silver's probably like $11 or $12 an ounce, so we'll say 1 ounce. That's like 28.35 grams or something of silver metal from a silver nitrate solution. All right, so we're looking for a time. We've got a mass that we're going to be working with. We know what our species is. We're going to be getting rid of the spectator ion when a current of, let's say, 2.4 amps is applied. All right. So I'm already not worried about the nitrates. That's a spectator. What's actually changing are the silver ions, 1 plus, and we have our silver 1 plus plus 1 electron giving us silver solid. And the whole point of that is to figure out that this is going to be our N when the time comes. I've got amps, and I guess I'm going to declare in advance that this is coulombs per second, just so I have that information available. I've got a mass here, and immediately I'm thinking, well, this is going to have to turn into moles, so I'll need the molar mass for that. The molar mass of silver happens to be 107.87 grams per mole. All right, and that's where I'm going to start out. Like, this is a lot of information, but if we start with something we know, like that mass, that was our end result of the process, so we need to work backwards and see where it would have started, how much time is required. So this is where I'll start. 28.35 grams of silver, right? An ounce of silver. We know that there's 107.87 grams per mole, and that's going to get me moles of silver. Grams are gone. And for every 1 mole of silver, this is an important part. Now we're relating that one step back to the number of electrons. There's 1 mole of electrons, right? That's where this number is coming from. So moles, silver, moles of electrons. where have I heard of moles of electrons before, or how am I going to relate moles of electrons to charge? Faraday's constant, right? For every 1 mole of electrons, there's 96,485 coulombs, right? So moles of electrons are gone. At that point, I want coulombs to go away, and I want to end up with a time, and I happen to have a unit that has both coulombs and time in it. It's that 2.4 amperes, 2.4 coulombs per second. So 2.4 coulombs per second. And again, I'm putting that there so that those units can cancel out. By dimensional analysis, it looks like I'm going to end up with seconds, which is where I want to be. And now we just need to punch it into the calculator. That calculation gives about 10,600 seconds, which translates to around 2.93 hours. All right. So the time required to precipitate 1 ounce of silver from a silver nitrate solution when applying the current that you might see from a typical cell phone charger, it's going to take about 2.93 hours. And it's interesting then to look at the rating on a lot of backup chargers, backup battery packs for cell phones, to see if indeed one of those could do that theoretically. Now in reality, you're going to have to worry about over voltages and all kinds of other things, resistance, so you're not going to get the full capacity of those battery packs. But in this particular case, it's a pretty simple example.